Alright, welcome back. Today we're going to be doing the 2022 AP AB Calculus FRQs, and as always there's going to be timestamps in the description and a link to the answers in case I didn't explain something more, you just want to double check. But starting off with this first one, we're told that from 5 a.m. to 10 a.m. the rate at which vehicles arrive is given by this function. Alright, and the first part is asking us to write but not evaluate an integral expression that shows a total number of cars that arrive between 6 a.m. and 10 a.m., which are t equals 1 and t equals 5 respectively. So we have the integral from t equals 1 to t equals 5 of that function, and then the differential with respect to t. You can write this and get the point. You could also write out the whole function. They accept both. It's just 1 point, so it's fairly simple. Alright, now the second part is asking you to find the average value of that rate. So it's going to be the same integral, except for the average value we're going to have 1 over the second bound, or the upper bound, minus the first bound, or the lower bound. So we're just going to have 1/4 of this integral. Oops, sorry, that's meant to be a 5, not a 4. And this is a calculator question, so you would just plug it into the calculator, and you should get something around 375.537. Something around that value and you'll be fine. But fairly simple. So far, it's nothing too crazy. That's part A and part B. Now for part C, it's asking about the rate at which the rate of vehicles is changing at t equals 1. So that means we're going to consider the derivative at 1. Now, obviously you could technically do this by hand, but why would you? It's a calculator question. So what you're going to do is just plug this into the calculator, find the derivative of it, and then plug in t equals 1 for the derivative, and you should get that the derivative at 1 equals 148.947. Alright, that's the first part of this. Now you have to figure out if it's increasing or decreasing, and then what we just did that, it's increasing because it's positive. But now, for the second point, we have to justify our answer. So you can write something along the lines of, because, or since, that the derivative at 1 is greater than 0, it's positive, a of t is increasing. So that right there will get you both points for part C. Alright, so far so good, although this last part's slightly tricky, it's actually not too bad. Alright, and now for part D, we're told that a line forms whenever a of t is greater than or equal to 400, and that the number of vehicles in the line is modeled by the function n of t, which is the integral from a to t of a of t minus 400 dt. It's a sloppy t, but that's okay. And now one key thing that we're told is that a represents when the line first forms. That's going to be very helpful later on. But what we're asked to find is the greatest number of vehicles in line on the interval a is less than or equal to t, less than or equal to 4. Okay? So it's a mouthful of a question, but when you break it down, it's actually not that bad. So the first thing we got to do is figure out, because we're looking for a maximum, we got to take the first derivative, right? So the derivative is just a of t minus 400, because this is an integral expression. Okay, and we know it's at a maximum, so this is going to equal 0. So we're looking for where a of t equals 400. Okay, this is where you're going to plug this into the calculator. You're going to get two distinct values where it equals 400. The first one we're going to call a, because that's what it is approximately 1.469. The second one is approximately 3.598. Okay, quick recap. We want the maximum of this function and we want that value. So we have to find where the derivative is equal to 0, and in that case it's where a of t equals 400, so use the calculator. Now, what we have to do is figure out which one of these is the maximum. How do we do that? We plug these two values back into this. Well, we know that the integral from a to a of t minus 400 is going to be equal to 0, because the integral from one point to that same point is just always 0. Okay, so that can't be it. So then let's try the integral from a to b of the same function. Oops. And now, this again is a calculator question. Please do not try to do this by hand. But what you're going to do now is just plug this into the calculator, and you should get approximately 71.254. Okay, but we're not done yet because there's one more point we have to check. Because it's the interval from a to 4. So let's check the integral from a to 4. And again, you're going to plug this into the calculator. Pro tip, you can just copy and paste this line of math essentially, and then just swap out the bounds to 4. And it'll save you a lot of time with calculator work. But once you plug it in, you should get approximately 62.338. Now out of these three, again, we're looking for a maximum, and it's this value. But because you can't have a car and some change of a car, some spare parts lying around, you can't have a car, and we're also asked to find the whole number, the maximum is 71 cars. And that concludes the first FRQ. Alright, now for the second FRQ, we're told the following information. F of x is ln of x plus 3, and g of x is x to the 4th plus 2x cubed. We are also given a graph of their functions, mine's poorly drawn. And we're told they intersect at 2 points, x equals -2 and x equals b, that's some positive number. We're not told that number. Alright, part A is asking us to find the area enclosed by both graphs, which is drawn here in red. Alright, so area, okay, we're going to do some integral. And we know that they intersect at -2, but now we need b. How do you get b? Well, what you're going to do in your graphing calculator, you're going to put in both of these functions, and once you've put them in, you're just going to find where they equal each other. And you should get b is approximately 0.782. So from here on out, whenever I write b, that's the number value that I'm referring to. Alright? So we have the integral from -2 to b. Well, one thing to notice, the graph of ln of x plus 3 is always above, while for this portion, g is underneath. So it's not f plus g of x, because then you're going to have a negative area, and it's actually going to be smaller than what it actually is. What it is the integral of f of x minus g of x, because what this means is you're essentially recognizing, hey, this area would be negative, but we don't want that. So you just subtract it, and then when you get the negative area, the negative turns into a positive. And now, once you plug this into the calculator, you should get a value of approximately 3.604. And that'll conclude the first part. Alright, now for part B, we're asked to find the function h, such that h is the vertical distance, which is shown here in blue. Alright, and now admittedly, this is a very math-wordy way to explain it, but what they're essentially just asking you to do is, okay, well, we know h is this, so it'll just be, at whatever point, it's going to be the value of f minus the value of g. Right, so we know h of x is just f of x minus g of x. And once you can understand that, the rest of this FRQ becomes fairly simple. Okay? But for this part, we're asked to find if h is increasing or decreasing at x equals negative a half. Okay, so that's a rate, we're going to need the derivative. So h prime of x is f prime of x minus g prime of x, h prime of negative 1/2. Now again, you can just plug this into the calculator. Don't try and do this by hand, it won't be very fun. But once you plug it in, you'll get h prime of negative a half equals negative 0.6. Now what does this tell us? This tells us that, okay, it's a negative number, so it's decreasing. So, since h prime of x is negative at x equals a half, negative a half. Alright, so since we know that h prime of negative a half is negative 0.6, we know it's decreasing. So you just gotta write it down. Something along the lines of, since h prime of x is negative at x equals negative 1/2, thus, or then, h of x is decreasing. Alright, now part C can look a bit tricky, but it's actually not that bad. So we're told that the region enclosed by f and g is the base of a solid, and the cross sections of that are squares, and we're asked to find the volume of it. Okay, so first things first, if we know that this area, the vertical lines, are the base, we know that that equals h of x, right? And to get the area of a square, it's just the base, or any length, squared, right? So now if we want to get the volume of that, which here's where the calculus comes in, we just have to integrate it from negative 2 to b. So, quick refresher, or redo, essentially. We're asked to find, assume that the difference between f and g is the base of a square cross-section to find the volume. Well, the difference between f and g is just h, right? Area of a square is just going to be the base squared. So in this case, it'll be h of x squared. And then, because it's a 3D object and we want the volume, we integrate it on the same bounds as before. Okay? So you're going to just plug this into the calculator, and you should get approximately 5.340. Not necessarily the easiest part to understand at first, but once it clicks and you realize it's just squares, get the area of them, then integrate, it does not become that difficult. It's actually. Now, part D of this FRQ is a bit wordy, but this is the gist of it. There's some vertical line, in this case, my expo marker. It is moving on the XY plane, left to right, along the base of the cross-section from part C, at a rate of 7 units a second, right? That's going to be important. So, what we're asked to find is the rate of change of the area of the cross-section with respect to the line, so we're going to have to care about the line, at the position of x equals negative a half. Okay, what does all that mean? Well, think about it like this. We know that area equals h of x squared, right? We want to find the change in area with respect to time. However, this is a function of x, not t. Right? So when you differentiate it, you're going to have 2h of x, and then chain rule it to get h prime of x. But hold on, this is just also in terms of x, so then you're going to have the change in x with respect to time. If it looks better like this, you could also just say dh dx, not dt. However you prefer it, but that's Once you can get to this equation, the rest of this FRQ is just calculator stuff and it clicks really easily. Right? So we're asked to find it at x equals -1/2. So we're going to have change in area with respect to time is just 2 times h evaluated at -1/2 times h prime evaluated at -1/2. But wait, we already got that from part B, right? So times -3/5 or 0.6, whichever you prefer, times, well, what's the dx dt? That's just how it's moving along the axis, which we were told is at a rate of 7. Now yes, you'd use your calculator to find h of -1/2, but once you plug this all in and you let the calculator do the work, you should get -9.722272, sorry. It is decreasing, but you're only asked to just find the rate of change, so just getting that value should be fine. And again, it's a bit wordy, but if you can understand how we got from this to this, it can quickly, because again, we know what the area is, we want the change with respect to time, so we have to chain rule this. So we have power rule 2h of x times the change in h with respect to x times the change in x, with respect to time to get eventually back to time. Alright, now for this third FRQ, we're given the graph of f prime of x and it looks something like this. We're also told that f of 4 equals 3, and that's all that we're given. So the first part is asking us to find f of 0 and f of 5. Okay, well, we have the derivative. How can we get back to the original function? We integrate, right? But we are not given an equation, we're given shapes. But wait a minute, the integral is the area under the curve, so we just have to find the area, and then we'll have the original function at certain points. Okay? So let's start with f of 0. Well, that's pretty much going to be the area underneath the semicircle. Alright? So, the area of a semicircle is just half the area of a circle, so it's half pi r squared. Okay? It has a radius of 2, so it's half pi times 2 squared. But one thing to note, because it is under the curve, it is negative. So this is the integral from 0 to 4 f prime of x dx. But we don't want the integral, we want the points. So when you do the math, this will come out to f of 4 minus f of 0, because that's how integrating a derivative works. Right? So we know, well, let's simplify this first. 2 squared is 4, times a half is 2, so you get negative 2 pi equals f of 4 minus f of 0. Okay? Now remember, f of 4 equals 3 from what they told us. Alright, now let's subtract 3 from both sides. You get negative 2 pi minus 3 equals negative f of 0. Multiply both sides by negative 1, you get 2 pi plus 3 equals f of 0. Alright, now f of 5 is easier to get, but it's the same process, where we're looking for the area essentially formed by this red triangle. Alright, so that'll be the integral from 4 to 5 of f prime of x dx. Okay, well, the area formula for a triangle is just half the base times the height. In this case, we have a base of 1 and a height of 1. So it's half times 1 equals, again, when you evaluate this integral, you're going to get f of 5 minus f of 4. Right? 1 times 1 is 1, times a half is a half. We don't know what f of 5 is, and we know f of 4 is 3. Add 3 to both sides, you should get 7 halves equals f of 5. Alright, now for the second part of this FRQ, we're asked to find all the points of inflection of the graph. So that's asking us to take the derivative of the graph, which in this case would be the second derivative, so that's where we want to be. So we're looking for where the slope equals 0. So at the apex of the circle, it'll be 0. And then again, up here, it'll be 0. So now how can we find those points? Well, the circle is centered at 2, 0. So we know that at x equals 2 and, well, this happens at x equals 6. At x equals 2 and 6, f of x has a point of inflection because the second derivative equals 0. And that is all you need to do for part B. Now for part C, we're told that g of x equals f of x minus x. And then we are asked to find on what intervals is g decreasing. So we're asked to find what's decreasing. That means we need g prime of x. G prime of x is just f prime of x minus 1. So we know this is going to be 0. But we're looking for where the x value is where it happens. So we're looking for where f prime of x equals 1. Alright? If you look at our graph, it's going to equal 1 right about there. And again here. However, we're not going to consider 7 because it's at the end point, which means we can tell what it's doing before but not after. So we won't be able to tell if it's increasing then decreasing or decreasing then increasing. Alright? So f prime of x equals 1 at x equals 5. Okay. So now we know where it has a critical point, but where does it decrease? Well, g prime is just f prime of x minus 1. So it's this graph just shifted down by 1. Right? Which means if this point was at 1, it's now at 0. And we can tell everything to the left of 5 is less than the function at 5. So essentially, this shifts all of this down by 1 and makes the semicircle and this triangle beneath the x-axis. Why does that matter? Well, if the first derivative is beneath the x-axis, the function is decreasing. So, from 0 to 5, g of x is decreasing because g prime of x is less than 0 at those values. Alright, now for part D, we're asked to find the absolute minimum value of g from part C. So to do that, well, in part C we found that x equals 5 is the only critical point. So now what we're going to do is the first derivative test to check whether it's a minimum or a maximum. So we have, it's going to be 0 at x equals 5. So now we're going to check g prime of 4, which is going to be f prime of 4 minus 1. Okay, f prime of 4 is 0, so g prime of 4 is just negative 1. Now let's check g prime of 6, which is going to be f prime of 6 minus 1. Well, at 6 it's 2. Alright, 2 minus 1 is 1. So g prime of 6 is 1. What does this mean? It means that it's going to look something like going down and then up, which is a minimum. That's what we want. Alright, now we just got to find the value at the minimum. So we're going to do g of 5 equals f of 5 minus 5. Okay, well from part A, we said f of 5 is 7 halves. Right? So you have 7 halves minus 10 halves. I just converted the 5 into halves. So g of 5 equals negative 3 halves. For this fourth FRQ, we're given a table that gives us the time and the rate of change of an ice sculpture in centimeters per day. Alright? The first part is asking us to approximate r double prime of 8.5. 8.5 lies in between 7 and 10. So what we're going to do is just take the 2-point slope, which will be negative 3.8 minus negative 4.4 over 10 minus 7. Right? It's an approximation of the slope. The slope would be a derivative. And this comes out to 0.2 centimeters a day. Now part B is also fairly straightforward. It's asking us if there's a time between 0 and 3 where r prime of t equals negative 6. Negative 6.1, that's pretty damn close to 6. Or sorry, negative 6. right? You're going to have negative 6.1, 6, and then negative 5. And we know our function is continuous, so it has to go through every value. So we know what's going to happen, but you have to justify it with something calculated. In this case, it would be the intermediate value theorem. So yes, since r prime of 0 is less than negative 6, and negative 6 is less than r prime of 3, so by the intermediate value theorem, IMT, I'm going to shorthand, exists a point such that r prime of t equals negative 6. Now for part C, we're asked to find a right Riemann sum to approximate the value of the integral from 0 to 12 r prime of t. So right Riemann sum using the interval, subinterval 0, 3, 3, 7, 7, 10, 10, 12. Alright, 3 minus 0 is 0, or sorry, 3 minus 0 is not 0, 3 minus 0 is 3. It'd be great if I could subtract, right? And because it's a right Riemann sum, we're going to use the right value, not the correct value. Oh, the right value would be the correct value, right? Then we have 7 minus 3 is 4, times the value at 7. 10 minus 7 is 3, times the value at 10. And then 10 minus 12 is 2, times the value at 12. And so you should get a line of math like this. You're going to have to do it, and then you should get an answer of negative 51. Alright, and now for part D, this is the trickiest part. However, it requires a bit of slowing down to fully understand. So we're given that the change in height with respect to time of a cone is decreasing at a rate of negative 2 centimeters. So dh dt is negative 2. At time equals 3, this is all given in the problem. The radius is 100 centimeters and the height is 50 centimeters. And we are now asked to find the change in volume at t equals 3. They do give us the volume formula, which is a third of times pi times r squared times h. Now, to differentiate this, it is both a product and a chain rule. Alright? So, dv dt, that's what we want, is, I'm going to take out the pi over 3 because that's just a constant. Then we have to find the derivative of r squared times h. Well, that's just the left derivative of the right. So r squared dh dt plus the right derivative of the left. Derivative of the left is 2r dr dt. Now, I'm going to pause there and just repeat this because this does take a minute to click. These are two different functions and they're being multiplied. So that's a product rule. But because they're functions, it's also a chain rule. Okay? Now from here, it is just plug and chug, and the answer at the end is nasty, so you don't have to find it. You can just leave it unsimplified, but let me show you. Right, so we're going to have pi over 3 dv dt equals pi over 3 times r squared, 100 squared, dh dt, negative 2, plus 2rh, 2 times 100 is 200, times 50. But wait a minute, we don't have dr dt, they didn't tell us it. It did. This is where this problem gets a bit trickier. Because dr dt is in the table. It's not in the question, so you have to look back to the table. Alright? So at time equals 3, dr dt is negative 5. That is where a lot of problems can arise. But once you see that, it clicks. And even if you don't see it, but you got up to here, you're still going to get a good amount of points. Alright? So if you were taking the test and you had this question, I would just write centimeters cubed a day, because that's the units, and leave your answer as that. Why would you simplify? If you want the simplified answer, it is negative 70,000 pi over 3 cubic centimeters a day. So, again, would you rather leave it as this and move on, or spend a couple minutes just to get that? I personally would just leave it as that and move on. Alright, now FRQ 5 starts off with a slope field, and you are asked to graph a particular solution to it. I'm gonna, with the magic of video editing, once again, display it up here somewhere. I'm sure my hands are gonna get cut off or something, but that's all you gotta do. Just, again, make sure you draw one line that goes through the point, doesn't go crazy with it. But yeah, fairly straightforward right there. Alright. Now the second part is asking us to write an equation for the tangent line from part A at the point 1, 2, and then use that equation to approximate f of 0.8. Okay, well, tangent line. How can we write a tangent line? Well, we have point slope form. Y minus y naught, some actual value, equals the slope times x minus x naught. Again, y naught, x naught, there's some actual value, they're not a variable. Okay? So what do we need for this? Well, first we gotta get the slope. And we can get that by plugging in the point into the derivative. So the derivative is this. 1/2 sine of pi over 2x times, it's a bit faded here, the square root of y plus 7. Okay? And we're asked to find we need to find the slope at 1, 2. So we're going to have 1/2 sine of pi over 2 times 1 is just pi over 2 times square root of 2 plus 7. Okay? Sine of pi over 2 on the unit circle, that's going to be up here. So it's going to be 1. Right? 1 times 1/2 is 1/2. So we have 1/2 times, alright, 2 plus 7 is 9, square root of 9 is 3. So we have 1/2 times 3, so that's going to equal 3/2. Alright? So y minus the point 2, because we're given this, equals 3/2 times x minus 1, again from the original point. And this is our tangent line. So now we can approximate 0.8. Right? So we're going to have y minus 2 equals 3/2 times 0.8 minus 1. Y equals 2 plus 3/2 times negative 0.2. And you can leave it at this if you're lazy, but if you want the simplified answer, this is 17 over 10. Alright, now for part C, we're told that the second derivative is always positive between -1 and 1. So now we're asked, is our approximation from part B an overestimate or an underestimate for f of 0.8? And to explain why. Alright, well, since its second derivative is positive, that means it's concave up, so it's going to open up, right? And we got our value to be a positive tangent line, so something like that. So if this is our tangent line approximation, and the function is actually something like that, that means the function might be up here, but we approximated it down here, right? So we actually underestimated. So what we would write is, since f double prime is greater than 0, our answer to part B, our answer from part B to part B is an underestimate. And now, not every AB class will cover this because it's a bit tricky, and this is worth 1 point out of 9 on this FRQ. So it's not the end of the world if you don't know it. And honestly, with this kind of FRQ, it's typically like that, because then you'll see shortly, but the next part is asking you to do some trickier integration. Not really tricky, but tedious and annoying at times. So it's just like, we'll make this worth a point, and then the hard math, which you should know and you should have learned, will be a lot more. So if you're good at that, you can make up for this lost point. But yeah, fairly straightforward, easy point. Alright, now for part D, we're asked to find a particular solution to our differential equation with the initial condition of f of 1 equals 2. Alright, so first thing we're going to notice, we have y and x on both sides. We don't want that. So we're going to divide by the square root of y plus 7 and multiply by dx to isolate our variables. So we get dy over root y plus 7 equals 1/2 sine of pi over 2x dx. Right? Now this looks like something we can integrate. Alright, I'm going to do the right hand side first. right? So we're going to have 1/2 the integral sine of pi over 2x dx. All right, this is going to be some u sub. We're going to let u equal pi over 2x. So du equals pi over 2x. Sorry, dx, not just x. But we only have dx. We don't have pi over 2 of dx. So 2 du over pi equals dx. Right? So now we're going to plug this back in. We have half the integral of 2 over pi sine of u du. Right? We can pull out this 2 over pi to get 1 over pi. All right, now the integral of sine is negative cosine. So we'll get negative 1 over pi cosine of u, but u equals pi over 2, pi over 2x, plus some constant. Right, so that's the right-hand side. All right. On the left-hand side is also going to be u sub. In this case, I'm going to use w, just so you could see that it's two different u subs. All right, but you also just use w or u again. So we're going to let w equal y plus 7. So now the change in w dw is just dy, right? So we have the integral of dw over the square root of w, and this can be rewritten as w to the negative 1/2 dw, right? So this just becomes a power rule, where you're going to add 1 and then divide by that. So it'll be w to the 1/2, then we're going to divide by 1/2, which is the same thing as saying multiply by 2. In this case, we're not going to have a constant of integration because we already have it on the right side. So we're going to have 2 square root of y plus 7. All right, and now this bottom line, or the one that I bracketed it off, is where we're going to solve for c. Okay? So we're solving for c at the condition that f of 1 equals 2. So wherever we see an x, we're going to plug in 1. Wherever we see a y, we're going to plug in 2. Okay? So we're going to have 2 square root of 2 plus 7 equals negative 1 over pi cosine of pi over 2 plus c. Alright? Well, let's look back at the unit circle, right? Pi over 2 is going to be way up here. Cosine is going to be 0 because it's just directly above the, it's on the y-axis. Sorry. Right? So we know this is going to all multiply to be 0. So it's just going to be c on the right-hand side, which is going to be nice. Then we have the square root of 2 plus 7. 2 plus 7 is 9. Square root of 9 is 3. Times 2, we're going to get 6. So c equals 6. Alright, that's going to be very helpful, because now we have to find a function where it's y equals. And then we'll be done with this FRQ. So I'm going to just rewrite this over here now with the initial condition given, or written down I should say. So 2 root of y plus 7 equals negative 1 over pi cosine of pi over 2 times x plus 6. Okay, let's divide both sides by 2 to get square root of y plus 7 equals negative 1 over 2 pi cosine of pi over 2x plus 3. Now we're going to square both sides to get y plus 7 equals negative 1 over 2 pi cosine of pi over 2x plus 3, whole thing squared. And now the last step is just subtract 7 to get y equals all of this mumbo jumbo. Let me write it out. Squared minus 7. Now, there's a lot of math, but I believe this part is worth 4 points, so it merits a lot of math compared to the previous parts, which are more straightforward and less work. But this will be your final answer here. I'm going to box it off in green. But this is a trickier part, but at the end of the day, if you can time manage, you can do it. Just make sure to slow down, think what they're asking you for, and remember that you can do calculus. You just gotta make sure you can read calculus. Alright, now for the final FRQ, we're given that particle P, the position of it is modeled by 6 minus 4 times e to the negative t. And that another particle, particle Q, the velocity is given by the velocity of Q with respect to, as a function of time, is just 1 over t squared, which is equivalent to t to the negative 2, which is what I wrote down here. The last piece of information we're given is that the position of Q at t equals 1 is 2. That will come in handy later. Alright? Now, for part A, we're just asked to find the velocity of the particle at time t, which just means a general function for the velocity. Okay? So, how do we go from position to velocity? Well, position is just some number, and velocity is a rate. So, we take the derivative with respect to time. So in this case, the velocity of P is going to be, well, root of 6, 0. And we're going to have the derivative of negative 4 e to the negative t. Well, we know because it's an e, we're going to keep it, right? Then derivative of the chain rule. So that would be the derivative of negative t, which would just be negative 1. So this would be plus 4. So the velocity of particle P with respect to t can be modeled by 4 times e to the negative t. Alright? Now for part B, we're asked to find the acceleration of Q and then find all times when the speed is decreasing. Okay, same thing. We're going to have to differentiate this. We'll get the acceleration of Q, the function of t, equals negative 2 times t to the negative 3. Alright? Now how do we figure out if the speed's increasing or decreasing? For the speed to be increasing, the velocity and acceleration have to agree on the signs. Okay? For the speed to be decreasing, they have to disagree on the signs. So, in this case, v, the velocity, will always be positive, while the acceleration will always be negative. So, because they always have different signs, particle Q is always decreasing in speed. So what you write is, since A of Q, AQ of t, is always less than 0, and VQ of t, the velocity, is always greater than 0, the particle Q, or just Q, is always slowing down. However you word it, just make sure you get the point across that because velocity and acceleration have different signs, the particle is slowing down. That's the main point you got to get across. Alright, now for part C, we are asked to find a general function for the position of particle Q. Okay? So to go from velocity to position, we have to integrate. So we're going to have negative 1 times t to the negative 1, right? Because when you integrate 1 over t squared, we're going to just treat this as t to the negative 2, right? And we're just going to power rule this to get negative t to the negative 1 plus c, right? So the position of particle Q versus as a function of t is just that. But we're told that at t equals 1, its position is 2. So we're going to plug in t equals 1 and y in the position equals 2 to get 2 equals negative 1 plus c. Add 1 to both sides. C equals 3. Alright? Now we just got to rewrite the equation. So you get the position of particle Q as a function of time is negative t to the negative 1 plus 3. So far this FRQ is fairly straightforward. Just please make sure to keep track of which particle is which. They denote it by saying the letter as a subscript. Now this last one, a little bit of thinking, but when it clicks, it's also fairly straightforward. As t goes to infinity, which particle will eventually be further from the origin? And we have to give a reason. Alright, so we're asking for the distance from the origin as t goes to infinity. Well, we can't really figure out the value at infinity. So this is where we're going to use the limit process. But what are we going to take the limit of? Well, we're asked for distance, so we're going to do positions. So for part D, we're going to have the limit as t goes to infinity of the particle p's position, and the same limit with the same t goes to infinity of what we just found from part C, which would be the position of particle q, right? So let's evaluate x first. We know that this is equal to this, so let's plug in infinity. No t's, so the only t that we're plugging into is up here. So we have e to the negative infinity, which is the same thing as 1 over e to the infinity, right? 1 over e to the infinity, the bottom is going to get bigger and bigger and bigger and bigger and bigger until it's pretty much just saying you're getting nothing. So this is equal to 0, right? So we're going to have 6 minus 4 times 0. 4 times 0 is 0. So the limit as t goes to infinity of particle p's position is equal to 6. All right? Now same thing, but with our answer from part C. Right? Well, we have to plug in t. We're going to have negative 1 over infinity. Same idea. The bottom is going to keep getting bigger and bigger and bigger and bigger forever. So it's just going to essentially be 0. So we're going to have this limit equals 3. And now, very simple question, which one's further, 3 or 6? It's going to be 6, right? So since the limit as t goes to infinity of particle p's position is greater than the same limit, just the other particle q, particle p goes faster, or further, not faster. That's all you need to do for part D. Once you figure out how you're going to do it with the limits t going to infinity and the positions, it's not too bad. This is just fairly straightforward with physics FRQ, but yeah, if you found this video helpful, please consider leaving a like. If you think I did a good job, subscribe, and if you have feedback, leave it in the comments. But otherwise, have a good day.